In 1963, inside a massive brick factory in Beloit, Wisconsin, Fairbanks Morse quietly delivered its final locomotive to the American rail market. It was a brutal end to an empire built on one of the most fascinating machines in American history, the opposed-piston diesel. A decade earlier, this exact engine architecture powered the U.S. Navy submarine fleet to victory in World War II. On land, their legendary Trainmaster locomotive unleashed 2,400 horsepower, shaking Midwestern rail yards and dominating in pure pulling force. But by 1963, the orders vanished. Mechanics in dusty rail yards refused to pull heavy upper crankshafts just to service lower cylinders. Fleet managers walked away. Railroads standardized around simpler machines, and the Beloit workforce lost the locomotive line that defined them. The paradox was clear. The Fairbanks Morse diesel never lost its power. It lost the world willing to maintain it. But the real story of Fairbanks Morse is not only the story of a lost locomotive war. It is the story of how America defined industrial trust and what happens when an engine built for the ocean is forced to survive in the dust. Every week, we tell the stories of American engines, factories, machines, and industrial names that once taught the country what power sounded like and what happened when the market moved on. Subscribe if that history matters to you. The story begins not with nostalgia, but with a specific place in Beloit, Wisconsin in the 1930s. Long before Fairbanks Morse tried to conquer the American rail yard, it had to conquer the American darkness. In the early 20th century, large parts of the United States were not connected to a centralized electrical grid. If a town in the Great Plains needed to pump municipal water, if a silver mine in Nevada needed to run a ventilation fan, or if a rural hospital needed a reliable generator, they could not wait for a transmission line. They had to make their own power on site. For decades, the Fairbanks Morse factory in Beloit, Wisconsin, sitting on the banks of the Rock River, was the place America called when it needed heavy, independent power. The company had started building windmills in the late 19th century, but as industrial demands grew, they shifted to internal combustion. By the 1920s, the Beloit foundry was a massive complex, pouring thousands of tons of molten iron to cast agricultural and industrial engines. They built the famous Z engine, a small, reliable farm motor, but their true ambition lay in heavy industrial power. To power a town or a factory, you needed a stationary engine. A stationary engine, a heavy internal combustion engine bolted to a concrete foundation to run pumps, generators, or mill equipment, was not built for speed, acceleration, or throttle response. In a rural American pump house, it was built for absolute unflinching reliability. It was expected to run at a steady RPM for days, weeks, or even months at a time without breaking a crankshaft or blowing a gasket. As the scale of American industry expanded, the market demanded a denser, cheaper-to-run form of power than early gasoline or kerosene motors. The answer was the diesel engine. A diesel engine, an engine that ignites fuel by compressing air until it becomes hot enough to burn diesel fuel, rather than using a spark plug, changed the economics of industrial work. In an American factory or a municipal power plant, a diesel meant cheaper fuel, massive torque, and an engine that could turn a heavy generator load without stalling. By the late 1920s and early 1930s, the Beloit plant was successfully building massive, traditional diesel engines, like their renowned Model 32. The Model 32 was a workhorse, known for a slow, rhythmic thump that echoed across rural America. But these machines were incredibly heavy and physically enormous. A standard stationary diesel of the era might stand 2 stories tall and weigh tens of thousands of pounds. The block, the main engine structure that holds the cylinders and major internal parts, had to be cast thick enough to contain the violence of diesel combustion. That immense size was perfectly fine if the engine was bolted to the thick concrete floor of a Midwestern power station. Space was not an issue in a prairie town, but in 1932, a different kind of customer came to Beloit with an impossible problem. The United States Navy was preparing for a new era of naval warfare. They were designing a new generation of fleet submarines, and they needed diesel power to run the boats on the surface and charge the massive battery banks. But a submarine hull is a steel pressure tube. Inside that tube, space is measured in inches. You could not fit a two-story stationary engine inside a fleet submarine. The engineering problem was severe. The Navy needed massive horsepower to propel the boat and run the generators. But they needed it in a footprint that was a fraction of the size of a standard industrial diesel. If the engine was too large, the submarine could not carry enough torpedoes, crew, or fuel. If the engine was too weak, the submarine would be too slow to survive on the surface. This was the engineering crisis of power density. Power density, the amount of power generated relative to the physical size and weight of the engine, was the ultimate currency in aviation and marine design. Standard diesel engines of the 1930s were large because they relied on a conventional layout. They had a heavy lower crankshaft, a row of vertical cylinders, and a complex heavy cylinder head bolted to the top. The cylinder head, the upper part of the engine that helps seal the cylinders and contains valves and combustion passages, was the structural bottleneck of early diesels. It had to withstand massive combustion pressure, it required complex valve trains, and it added significant height and weight to the top of the engine block. If a manufacturer wanted more power out of a conventional block, they usually added more cylinders, which made the engine longer. Or they made the cylinder bore wider, which made the engine wider. Or they increased the stroke, which made the engine taller. Every traditional solution meant more iron, more weight, and a larger footprint. The engineering team at Fairbanks Morse looked at the standard diesel architecture and realized that optimizing it would never meet the Navy's demands. A traditional engine was simply too tall for the curve of a submarine hull, and a V-type engine was often too wide to leave room for the crew to walk past it in a cramped engine room. They needed a radical alternative. The Beloit engineers were aware of European experiments with opposed-piston designs, specifically the Junkers-Jumo aircraft engines in Germany, which used a completely different way to burn fuel. But the German engines were built for airplanes. They were lightweight, highly stressed, and complex. Fairbanks Morse needed to take the theoretical opposed-piston concept and translate it into heavy, unbreakable American industrial iron that could survive months at sea. They set up a development program in Beloit, backed by Navy funding. The goal was to build an engine that defied the standard rules of diesel manufacturing. They would eliminate the heaviest, most problematic parts of the conventional diesel engine. The engineers in Beloit did not look for a better way to cast a cylinder head. They decided to build a diesel engine that didn't need a cylinder head at all. The machine that emerged from the Beloit factory was designated the Fairbanks Morse 38D818. The name was simply a measurement of its bore, the 8 1/8 inch diameter of its cylinders, but the architecture behind that number was a radical departure from standard American industrial iron. To solve the Navy's demand for massive power in a narrow space, the engineers finalized an opposed-piston engine. An opposed piston, or OP engine, is an engine layout where two pistons share a single vertical cylinder, facing each other and squeezing the combustion space exactly in the middle. Because there was a piston sealing the top of the cylinder and another piston sealing the bottom, the engine did not have a cylinder head. The cylinder head, the heavy iron casting that caps a traditional engine and holds the valves, was entirely eliminated. In a conventional heavy diesel, the cylinder head took the absolute worst abuse of the combustion cycle. It was prone to cracking, it required complex valve trains, and it added massive weight and height to the top of the block. By erasing the cylinder head, Fairbanks Morse erased one of the most vulnerable parts of early diesel design, but removing the top of the engine created a new mechanical reality. To harness the power of that upper piston, the OP engine required two crankshafts. A crankshaft, the heavy rotating shaft that turns the up and down motion of the pistons into rotational twisting power, is normally found only at the bottom of an engine. The Fairbanks Morse OP had one heavy lower crankshaft sitting in the oil pan and a second upper crankshaft running across the very top of the engine block. When the fuel injectors sprayed diesel into the center of the cylinder, the violent expansion of combustion pushed the two pistons apart simultaneously. The bottom piston pushed down on the lower crankshaft, and the top piston pushed up on the upper crankshaft. The two rotating shafts were perfectly synchronized by a massive vertical gear drive running down the front of the block. This was not just a clever mechanical trick, it was a masterpiece of power density. By stacking the pistons vertically and removing the cylinder head, Fairbanks Morse packed a massive amount of displacement. The total volume swept by the pistons, which dictates how much air and fuel an engine can burn, into an incredibly narrow footprint. Furthermore, it was a two-stroke engine. A two-stroke engine, an engine that completes a power cycle every time the pistons come together, rather than waiting for four separate strokes to intake, compress, ignite, and exhaust, allows a machine to make explosive power much faster for its size. Because it lacks standard intake and exhaust valves, the OP engine breathed through ports cut directly into the cylinder walls. As the pistons moved apart, they uncovered these holes. A mechanically driven supercharger, a device that forces compressed air into the engine, blasted fresh air into the top ports, which violently pushed the burnt exhaust gases out through the bottom ports. To understand why this mattered, you have to picture where these engines went to work. Inside an American Gatto-class or Balao-class fleet submarine during World War II, the engine room was a steel tube submerged in the Pacific Ocean. It was packed with pipes, high-voltage lines, and oppressive heat. In this claustrophobic environment, mechanics walked on steel deck plates with only inches of clearance on either side. A traditional V-type diesel engine would have been too wide, blocking the narrow walkways. A traditional inline engine would have been too tall, scraping the pressure hull. But the Fairbanks Morse 38D8-1 was tall and incredibly narrow. Four of these towering engines could sit shoulder to shoulder inside the submarine's hull. In this theater, horsepower, the measurement of how quickly an engine can do work, was not about top speed. Submarines used their diesel engines while running on the surface to turn heavy generators, which charged the massive battery banks that powered the boat underwater. The faster the engines could run those generators, the faster the submarine could dive back into the safety of the dark. The opposed-piston engine allowed American submarines to charge faster, run further, and survive longer. The Beloit foundry transformed into a relentless war production machine. The machining lines ran day and night, cutting the complex vertical drive gears and balancing the twin crankshafts. It was an engine that required high-precision manufacturing, and the Midwestern workforce delivered it. By the end of the conflict, Fairbanks Morse OP diesels powered roughly half of the entire U.S. Navy submarine fleet. The engine earned a reputation for absolute reliability. Fleet trust in the OP was unshakable because in the Pacific, a blown engine often meant a lost crew. But that trust was also built on a specific military reality. In a naval shipyard, maintenance was performed by highly trained specialists with access to heavy overhead cranes, unlimited parts, and infinite labor hours. If an upper crankshaft needed to be removed, a crane simply lifted it out of the hull. When the war ended in 1945, the Beloit plant was operating at peak capacity. Fairbanks Morse looked at the opposed piston engine and realized they possessed the most battle-tested, power-dense heavy diesel in the country. By the late 1940s, Fairbanks Morse was not just a manufacturer, it was an industrial titan running at maximum capacity. The Beloit foundry was pouring iron around the clock. The opposed piston engine had proven itself in the most hostile environment on Earth. But the post-war American economy was changing, and the greatest mechanical transition in the country's history was happening right outside the factory doors. The American railroad was trading steam for diesel. A locomotive diesel, a large diesel engine used in a locomotive to generate or transmit power for rail movement, was fundamentally different from the steam engines it replaced. It did not turn the drive wheels mechanically with steam pressure. Instead, the massive diesel engine spun a generator, creating high-voltage electricity that powered traction motors on the axles. It was a rolling power plant. The American rail market was already being dominated by the Electromotive Division, EMD, a branch of General Motors, and the American Locomotive Company, ALCO. EMD had a massive head start and an expansive factory network, but Fairbanks Morse looked at their OP engine and saw a mechanical advantage that neither GM nor ALCO could match. Pure, concentrated power density. In an America where an engine could decide whether a field was cut, a truck made its delivery, A boat left the dock, a generator carried a hospital through a storm, or a train moved freight across a continent. Power was not an abstraction. It was iron, fuel, labor, heat, sound, repair, and trust. Fairbanks Morse believed they had the ultimate iron. They began placing the 38D8 or 1-8 submarine engine inside heavy locomotive carboties. Because the Beloit plant was initially overwhelmed with leftover Navy orders, their first major units in 1945, the sleek Erie-built passenger locomotives, were actually assembled by General Electric in Erie, Pennsylvania. But by the dawn of the 1950s, the Beloit facility had transformed into a fully integrated locomotive assembly plant. The factory floor became a cathedral of heavy manufacturing. Massive overhead cranes carried the tall, narrow OP blocks down the machining lines. Mechanics who had learned their trade building submarine power plants were now dropping those same heavy castings into steel locomotive frames. The company aggressively expanded its railroad catalog, culminating in 1953 with the release of a machine that shattered the limits of American freight hauling, the H-2466, universally known as the Trainmaster. The Trainmaster was an absolute brute. While a standard EMDF unit of the era might produce 1,500 horsepower, the Trainmaster unleashed a verified 2,400 horsepower from a single towering opposed-piston engine. It was at the time of its launch the most powerful single-engine diesel locomotive in the world. To understand the shock of this machine, you have to picture an American rail yard in 1953. In places like the Appalachian coal routes operated by the Virginian Railway, or the dense freight corridors of the Pennsylvania Railroad, pulling heavy tonnage up steep grades was a brutal mathematical equation. More weight required more locomotives hooked together, which meant higher fuel costs and more crews. But the Trainmaster changed the math. A single Fairbanks Morse locomotive could often do the work of two competing machines. The engine block itself was a towering monument to American cast iron. The 12-cylinder version of the OP engine used in the Trainmaster displaced over 12,000 cubic inches. Every time the massive pistons moved toward each other, they squeezed the diesel fuel into a violent explosion that pushed the twin crankshafts with immense unyielding torque. Torque, twisting force often felt as the pulling strength of an engine, was exactly what the railroads bought. They were not buying top speed. They were buying the ability to move 10,000 tons of coal from a dead stop on a wet rail. The sound alone was unforgettable. Because it was a two-stroke OP engine without standard exhaust valves, the exhaust note was not a typical diesel chug. It was a rapid, tearing roar, a high idle scream that echoed across Midwestern plains and eastern mountains. When a Trainmaster notched up under a heavy load, it shook the ground with a violence that railroad workers had never experienced from a diesel. The Virginian Railway bought them to haul coal. The Southern Pacific bought them to conquer steep mountain passes. For a brief, shining moment in the 1950s, Fairbanks Morse convinced the industry that power density was the only metric that mattered. The badge had found its believers. The industry had not yet shown the price. While the Trainmaster locomotive captured the headlines and the imagination of the American railroad industry, the true scale of the Fairbanks Morse empire extended deep into the invisible infrastructure of the country. The railroad was the most visible battlefield, but the Beloit plant was also feeding a massive demand for stationary power. A stationary engine, a heavy internal combustion engine permanently bolted to a concrete foundation to run pumps, generators, or mill equipment, was the unseen heartbeat of mid-20th century America. In the 1950s, not every rural county or isolated industrial site was fully supported by a reliable national electrical grid. They needed independent baseload power. Fairbanks Morse opposed-piston engines were shipped by the hundreds to municipal power plants, rural electrification cooperatives, and massive municipal water districts. Because the OP engine packs so much displacement into such a narrow vertical footprint, a city could fit 3 or 4 massive generator engines into a brick pump house that would have previously only held one conventional V-type diesel. Picture a municipal pumping station in the Midwest during a violent spring flood in 1955. The primary grid fails. The lights in the facility go dark. In the basement, a Fairbanks Morse 38D8 1-8 generator engine automatically fires. Because it is a two-stroke engine, producing power on every inward squeeze of the pistons, it reaches operating RPM almost instantly. The massive vertical gears howl, the The twin crankshafts take the immense load, and the city's flood control pumps keep turning. The citizens above never hear the engine, but their homes remain dry because a submarine engine from Beloit was waiting in the dark. By the mid-1950s, the Fairbanks Morse factory in Beloit was operating at a staggering scale. The complex covered dozens of acres along the Rock River. It employed over 5,000 workers, operating its own foundries, machining centers, and assembly halls. It was a self-contained industrial city. The workforce cast the iron, machined the complex twin crankshafts, cut the vertical drive gears, and assembled the towering blocks. The town of Beloit was entirely synchronized with the shifts of the factory. When the whistle blew, the streets filled with machinists and foundrymen who knew they were building the most power-dense heavy machines on Earth. They were not just building locomotives and generators. The OP engine remained a dominant force in civilian and military marine applications. Tugboat operators, icebreakers, and Navy vessels relied on the engine because a tugboat hull, much like a submarine, offered very little lateral space. A narrow engine meant more room for fuel, which meant more days at sea. In an America where an engine could decide whether a field was cut, a truck made its delivery, a boat left the dock, a generator carried a hospital through a storm, or a train moved freight across a continent, power was not an abstraction. It was iron, fuel, labor, heat, sound, repair, and trust. For Fairbanks Morse, that trust was built on the sheer, undeniable physical strength of their machine. Their engines moved the heaviest coal drags over the Appalachian Mountains. Their generators kept isolated towns illuminated. Their marine diesels pushed cargo through freezing harbors. The Beloit engineers had taken an experimental, highly complex European aviation concept and turned it into a monument of American heavy manufacturing. They had conquered the ocean, and for a few glorious years in the early 1950s, it looked as though they were going to conquer the American rail network. The trainmaster had proven that Fairbanks Morse could pull more freight than anything on the rails, but a railroad does not only measure an engine by how it pulls, it measures it by how it bleeds. The first crack in the Fairbanks Morse locomotive empire was not a catastrophic engine failure on the main line. It was not a sudden loss of power dragging coal up an Appalachian grade. The first crack was almost invisible to the public. It happened in the heavy, oil-stained air of a Midwestern rail yard when a mechanic opened a service manual, looked at a scored lower cylinder on a Fairbanks Morse engine, and realized how many hours it was going to take to fix it. An engine does not only live on the tracks or in the pump house, it lives in the service network. A service network, the mechanics, parts counters, specialized tools, and repair culture that keep a machine running after it leaves the factory, is often the true test of industrial survival. Fairbanks Morse had built an engine of staggering power, but they were about to learn a brutal lesson about American maintenance. To understand the problem, you have to look at how the opposed-piston engine was originally designed to be serviced. When the Navy used the 38D8-18 in a submarine, they knew it was a complex machine. But in a naval shipyard, maintenance was an orchestrated military operation. If an engine needed a major overhaul, a major service process where an engine is taken apart, inspected, and rebuilt to operating standards, the Navy simply brought the submarine into port. A massive overhead crane reached into the hull, unbolted the entire upper crankshaft, or simply lifted the entire engine block out of the boat and set it on a pristine shop floor. The Navy had specialized tools, infinite labor hours, and a budget underwritten by the federal government. The American railroad operated in a completely different reality. In a commercial rail yard, time was the only metric that mattered. A locomotive sitting in a repair bay was a machine burning money. Railroads ran on razor-thin margins, and their mechanics worked in dirty, high-pressure environments, often exposed to the elements or working inside dark, cramped roundhouses. When a standard Fairbanks Morse OP engine needed routine lower cylinder maintenance, the mechanical layout became a nightmare. Because the cylinders were shared by two pistons, you could not simply pull a cylinder head off the top of the engine to reach the combustion chamber, because there was no cylinder head. Instead, to access a lower piston or a liner, mechanics often had to disassemble the top half of the engine. They had to open the roof hatches of the locomotive. They had to unbolt the heavy covers. They had to disconnect the massive vertical drive gears that synchronized the top and bottom of the engine. And then they had to pull the entire upper crankshaft, the heavy rotating shaft that sat at the very top of the block. It was an agonizing, labor-intensive process. A repair that might take hours on a conventional engine took days on a Fairbanks Morse. The mechanics hated it. And in the heavy equipment industry, when the mechanics hate a machine, the fleet managers quickly follow. This maintenance burden might have been acceptable if Fairbanks Morse was the only option for diesel power, but they were fighting a war against the most ruthless manufacturing force in America, General Motors. GM's electromotive division, or EMD, did not build an opposed-piston engine. They built the 567, a conventional V-type, two-stroke diesel. The 567 was not as power-dense as the Fairbanks Morse OP. It was wider, it was heavier per horsepower, and it did not have the exotic submarine pedigree. But the 567 was designed from the ground up for the brutal reality of the American rail yard. EMD used a modular design concept called the power assembly. A power assembly, a self-contained engine component that includes the cylinder liner, the piston, the connecting rod, and the cylinder head all bolted together as one unit, changed the entire culture of railroad maintenance. If an EMD 567 dropped a valve or scored a piston, a rail yard mechanic did not have to dismantle the entire engine. Two mechanics could unbolt the single broken power assembly, lift it out with a basic hoist, drop a fresh one in, and have the locomotive back on the revenue track by the end of the shift. The contrast was devastating. Fairbanks Morse was selling absolute horsepower. EMD was selling uptime. Fleet managers sat in their offices with maintenance spreadsheets, and the math was undeniable. A Fairbanks Morse trainmaster could pull more freight cars than an EMD-F unit. But the trainmaster spent significantly more time torn apart in the repair bay, accumulating massive labor costs. The pure mechanical strength of the opposed piston engine, its incredible power density, its lack of cylinder heads, its twin crankshafts, had become the very thing that made it too expensive to keep on the rails. By the late 1950s, the momentum shifted. The major railroads began to standardize. Standardization was a financial defense mechanism. If a fleet bought exclusively from EMD, they only needed one type of service manual, one set of parts in the bin, and one training program for their mechanics. Every time a railroad chose to standardize around General Motors, Fairbanks Morse lost another slice of the market. The Beloit factory was still pouring iron, but the orders for new locomotives began to thin out. The legendary Trainmaster, despite its record-breaking 2,400 horsepower, sold only a little over 100 units. The railroads simply could not afford the maintenance penalty. The engine had not lost a single horsepower. It was simply losing the war of the American repair bay. As the 1950s drew to a close, the American railroad industry entered an era of ruthless corporate consolidation. Corporate consolidation, the process where companies merge, acquire, or absorb other companies to survive, changed the way America moved freight. Small independent railroads were swallowed up by massive conglomerates. And when railroads merged, they demanded uniformity. Fleet managers did not want three different types of diesel engines in their repair shops. They wanted a single, predictable standard. General Motors offered that standard with their EMD locomotives. GM also offered something that Fairbanks Morse simply could not match: the financial backing of the largest corporation in America. EMD could offer aggressive financing and guaranteed trade-in values. Fairbanks Morse, an independent heavy machinery builder in Wisconsin, could not subsidize their locomotives in the same way. The service network collapsed quickly. A service network relies on volume. If there are thousands of EMD engines on the rails, every parts counter, distributor, and machine shop in the country will stock EMD parts. Because Fairbanks Morse sold fewer locomotives, parts became harder to find. If a trainmaster broke down in a remote Ohio rail yard, it might sit for days waiting for specialized opposed piston parts to arrive from Beloit. A locomotive sitting idle was a financial disaster for the railroad. By the early 1960s, the mighty trainmasters and the earlier Fairbanks Morse models hit their first major overhaul cycles. An overhaul cycle is the point in a heavy engine's life where it must be completely disassembled, inspected, and rebuilt to restore its original power. When the railroads looked at the required labor hours to pull the upper crankshafts out of an OP engine, they ran the math. It was cheaper to buy a brand new EMD locomotive than it was to pay their mechanics to rebuild a Fairbanks Morse. The scrap lines began to fill with the most powerful single-engine diesels in the world. Locomotives that were less than 10 years old were towed to salvage yards and cut up with blowtorches. The massive cast iron blocks, the twin crankshafts, and the complex vertical drive gears were melted down. The American Railroad had decided that power density was useless if it could not be serviced cheaply. In 1963, inside the massive brick assembly halls in Beloit, the workforce finished their final domestic locomotive. It rolled out of the factory doors and into a market that no longer wanted it. Fairbanks Morse quietly exited the American locomotive business. The loss of the rail market broke the independence of the company. Fairbanks Morse, a titan of American industrial power, could not survive the financial blow of the locomotive failure alone. In 1964, the company was acquired and merged into Colt Industries. Brand dilution, the weakening of a brand when the name remains but the original identity changes, immediately followed. The Fairbanks Morse badge remained on the side of the factory, but the company was now just a division of a larger corporate conglomerate. The era of the independent Beloit engine empire was over, but the opposed-piston engine itself did not die. The machine was too well engineered to vanish entirely. It simply retreated from the dusty, cost-cutting world of the American rail yard and returned to the environments that actually valued its power density. The Navy still needed it. Municipal pumping stations still needed it. Backup generator rooms and critical infrastructure facilities still needed it. In these spaces, mechanics did not mind pulling an upper crankshaft because they had the time, the overhead cranes, and the maintenance budgets to do it right. The engine had failed on the rails, but it remained deeply embedded in the hidden infrastructure of the country. The problem was not the engine. The problem was the world that tried to use it. The Fairbanks Morse story is the ultimate proof that American industrial survival requires more than just mechanical strength. An engine must survive the mechanics who fix it, the fleet managers who buy it, and the accountants who measure its cost. The block was still solid. The maintenance was too hard. The fleet standardized. The orders stopped. The factory lines shifted. The brand was sold. The rail yards went quiet. The locomotive empire was gone. But deep inside the American grid, in places where maintenance was planned and space was tight, the heavy iron from Beloit refused to stop turning. The story of American engine empires is usually a story of total collapse. A factory closes, the tooling is sold for scrap, the blueprints are lost, the dealer network dissolves, and the badge becomes nothing more than a plastic emblem on a collector's shelf. But the Fairbanks Morse opposed-piston engine defied the standard American industrial autopsy. The machine was not defeated by a flaw in its engineering. It was defeated by the brutal labor economics of railroad maintenance. Once the engine was removed from the dusty, high-pressure environment of the commercial rail yard, it simply went back to doing what it was originally designed to do. Today, the massive brick facility in Beloit, Wisconsin, is not an abandoned ruin. It is still an active, heavy manufacturing center. Now operating under the name Fairbanks Morse Defense, the company still casts iron. They still machine heavy parts. And remarkably, nearly a century after the Beloit engineers first sketched out a diesel without a cylinder head, they are still building the opposed piston engine. When the United States Navy commissioned the amphibious assault ship, a USS Macon Island, in 2009, they did not rely on unproven technology for their emergency backup power. Deep inside the hull of that modern warship, they installed Fairbanks Morse diesels. The Navy knew what the mid-century railroad fleet managers had forgotten. When absolute survival is the only metric, and when a military budget can support the maintenance hours, nothing beats the pure power density of an OP block. But the legacy of Fairbanks Morse is not just a story of modern military contracts. It is preserved across the American landscape by a dedicated network of industrial historians, mechanics, and museum curators. While the massive 2,400 horsepower trainmasters were ruthlessly scrapped, a few smaller Fairbanks Morse switchers, like the rugged H-1244, survived in private industrial rail yards, where their heavy weight and low-speed pulling power were perfect for moving steel or grain. Today, at places like the Illinois Railway Museum or the Mid-Continent Railway Museum, volunteer mechanics spend thousands of hours tracking down rare opposed piston parts, sharing old oil-stained service manuals, and pulling upper crankshafts just to keep these surviving locomotives running. When one of these museum pieces fires up, sending a thick plume of two-stroke smoke into the sky and settling into that rapid, tearing idle, the crowd hears a sound that was completely erased from the commercial main line by 1963. This preservation is not just mechanical nostalgia. A running Fairbanks Morse engine is a physical argument about a time when American manufacturing pushed the absolute limits of thermodynamic efficiency without the help of computer modeling. It is a monument to the mid-20th century machinists who cut massive vertical drive gears by hand, and to the foundry workers who poured blocks of iron the size of small houses. When restorers pull the heavy steel access covers off a surviving OP engine today, they are preserving a mechanical philosophy. They are keeping alive a machine that forced America to ask what mattered more: the ultimate pulling power of a locomotive or the ease of fixing it on a Tuesday night in a freezing rail yard. General Motors won the economic war, but Fairbanks Morse left behind the more fascinating machine. The most profound part of the Fairbanks Morse legacy is that you do not need to visit a museum or a Navy base to find one. Across the American Midwest and along the floodplains of the South, there are massive municipal pumping stations and emergency backup generator facilities that were built in the 1950s. Inside these concrete bunkers, hidden from public view, sit rows of original Fairbanks Morse 38D8-18 opposed-piston engines. They are not museum pieces. They are active, working relics. They are tested monthly by city mechanics. When the primary electrical grid fails during a catastrophic storm, these 70-year-old two-stroke diesels are still expected to fire up instantly, spin the massive generators, and keep the floodwaters from destroying an American city. There is even a surprise footnote to the Beloit engineering legacy. In recent years, as the global engine industry has faced increasingly strict emission standards and fuel economy pressure, modern automotive and aviation startups have begun looking backward. Engineers are currently developing new computer-controlled opposed-piston engines, attempting to utilize the exact same thermal efficiency advantages that Fairbanks Morse capitalized on in the 1930s. By eliminating the cylinder head, modern engineers hope to reduce heat loss and lower emissions. The Beloit foundry was simply 90 years ahead of the software needed to perfect it. America remembers the engines that were parked in its driveways. It remembers the small engines that cut its suburban lawns, the V8s that idled at its drag strips, and the conventional diesels that hauled freight down the interstate. Those machines were highly visible. They belonged to the consumer. Fairbanks Morse lived in the shadows. It powered the grid, it powered the Navy, and for a brief, violent moment, it tore across the American rail network with a high idle scream that no railroad worker would ever forget. It lost the public, but it kept the critical infrastructure. It was an empire built on iron, driven by a pair of massive crankshafts and designed for a world where failure was simply not an option. Somewhere in the American Midwest, inside a dark concrete municipal pump house, a heavy oil-stained Fairbanks Morse service manual still sits on a metal workbench. It rests next to a towering windowless iron block, a submarine engine that has been waiting in the dark for 60 years, ready to shake the floorboards on the very first crank. See you in the next one.